Gold never rusts, because unlike iron, it does not react with atmospheric oxygen. This is because chemical reactivity varies across metals. Scientists have arranged metals in a series based on their chemical reactivity. In this lesson, you will learn about the arrangement of metals in an activity series based on their reactive properties. You will also learn how the positions of metals in an activity series impact the process of extraction from their respective ores. You will learn in particular about the extraction of aluminium from its ores. At the end of this lesson, you will be able to illustrate through an experiment the differences in reactivity of metals, analyze activity series of metals, describe various techniques for the extraction of metals, illustrate the process of reduction with examples, describe the process of extraction of metals by electrolysis, analyze the position of aluminium in the activity series, describe the process of extraction of aluminium from bauxite, and list the uses of aluminium. You can observe the differences in reactivity of various metals through an experiment. Take samples of 4 metals: sodium, magnesium, calcium, and copper in different test tubes. Add 2 ml of dilute hydrochloric acid or sulfuric acid to each of these samples. The reaction of the acid with the metal will yield a salt and hydrogen gas in each test tube. However, you will notice that the rate at which the gas is liberated in each test tube is different. For instance, adding 2 ml of dilute hydrochloric acid to sodium results in a vigorous liberation of hydrogen gas. If you hold a burning splinter over the mouth of the test tube, the flame is extinguished with a pop sound. Similarly, the addition of dilute hydrochloric acid to magnesium in the second test tube liberates hydrogen. However, the rate at which hydrogen is liberated in this case is lower than that observed in sodium. The rate of liberation of hydrogen reduces further in the reaction with calcium, while copper does not react with hydrochloric acid at all. The variation in the rate of liberation of hydrogen indicates that the metals differ in their reactivity. To predict the reactions of given metals with other elements, scientists developed a system where metals were arranged in decreasing order of their reactivity. This arrangement of metals is called the activity series of metals. Thus, in this series, the most reactive elements are at the top and the least reactive elements are at the bottom. For example, potassium at the top of the series is the most reactive among all the elements in the series. For any 2 metals in the series, the metal placed higher in the series can displace the other metal from its salt solution. For example, zinc displaces copper from copper sulfate solution to form zinc sulfate. As you move down the series, oxides of highly reactive metals like magnesium and aluminium are not reduced easily either by hydrogen, carbon, or carbon monoxide. This is because the ionic forms of magnesium and aluminium are more stable than their atoms. Moving further down, metals that are placed below copper do not rust easily because of their low reactivity. A number of metals are available only in combined forms as ores. To obtain the pure forms of these metals, we need to extract them from their respective ores. Based on the reactivity displayed by metals, They can be extracted through the following methods: reduction and electrolysis. Reduction is the process of removal of oxygen for extraction of metals from their oxide ores. The common reducing agents used for reduction of metal oxides are carbon monoxide, carbon, hydrogen. For example, iron oxide is reduced to iron by carbon monoxide. Iron oxide is reduced to iron using carbon as the reducing agent. Similarly, copper oxide is reduced to copper using carbon. Copper oxide is reduced to copper using hydrogen. The metals high up in the activity series are very reactive. Hence, they cannot be obtained from their compounds by heating with common reducing agents like carbon, carbon monoxide, and hydrogen. For example, a reducing agent like carbon cannot reduce the oxides of metals like sodium, magnesium, calcium, and aluminium because they have more affinity for oxygen than carbon. Therefore, these metals are refined by another method known as electrolysis. Electrolysis is the process of the decomposition of a substance by passing electricity through it in a molten or dissolved state. Consider magnesium chloride ore. Magnesium is highly reactive and therefore cannot be reduced by common reducing agents like carbon, carbon monoxide, and hydrogen. Therefore, magnesium is extracted by electrolysis. Electrolysis of fused magnesium chloride gives magnesium at cathode and chlorine at anode. During the reaction at cathode, the reduction of magnesium chloride occurs due to gain of electrons. Magnesium ions gain electrons forming magnesium atoms. During the reaction at anode, chloride ions get oxidized due to loss of electrons. Thus, chloride ions lose electrons to form chlorine atoms. Chlorine atoms combine to form chlorine molecules. Thus, as a result of electrolysis of magnesium chloride, magnesium metal is deposited at the cathode, and chlorine is liberated as a gas at the anode. Let's now take up aluminium, a well-known metal in the activity series, and analyze its properties as well as the method for its extraction. Aluminium is a highly electropositive element and so forms positive ions. Therefore, it is placed towards the top and below magnesium in the activity series. It is not viable to use carbon reduction as a method for extraction of aluminium because the metal needs to be heated to very high temperatures in this method. Therefore, aluminium is extracted from its ores using electrolysis. Important ores of aluminium are bauxite, represented by the formula Al2O3 2H2O, corundum, represented by the formula Al2O3, and cryolite with the formula Na3AlF6. Bauxite is the principal ore of aluminium. The extraction of aluminium from bauxite involves 3 steps. First, the purification of bauxite using Cbse process. Next, the electrolytic reduction of anhydrous Al2O3 by Hall and Herold's process. The last step is the purification of impure aluminium by Hope's process. The first step in the extraction of aluminium is the purification of bauxite through a process called Cbse process. This process is named after Austrian chemist Carl Bayer, who invented and developed the method to supply alumina for the textile industry. Iron oxide is present as an impurity in bauxite. In Bayer's process, this iron oxide is removed by treatment of bauxite with sodium hydroxide solution. Purification of bauxite involves 3 steps. In the first step, aluminium oxide is allowed to react with sodium hydroxide to form sodium meta-aluminate. In the second step, sodium meta-aluminate is diluted with water to form aluminium hydroxide. In the third step, aluminium hydroxide is heated strongly to form aluminium oxide. The second step in the extraction of aluminium is the electrolytic reduction of alumina obtained using Bayer's process. This is done through Hall and Herold's process. Hall and Herold developed the process independently. The electrolytic cell used in this process has the following components: an iron tank lined on the inside with carbon, which acts as the cathode, a series of carbon rods that act as the anode, alumina Al2O3 as the electrolyte. Fluorspar and cryolite are mixed with the electrolyte to increase its electrical conductivity and decrease the fusion temperature. In the electrolytic process, electricity is passed through the electrolytic cell. Sodium, aluminium, and calcium ions migrate towards cathode. The aluminium ions discharged at the cathode sink to the bottom of the tank and are periodically tapped off. The oxide ions lose electrons and form oxygen atoms at the anode. The oxygen atoms combine and form oxygen molecules. The metal obtained after Hall and Herold's process is about 98% pure. This needs to be purified further. The third step is purification of the electrolyzed output from Hall and Herold's process. This is done by using a cell developed by Hope. Therefore, the process is called Hoop's process. Hoop's cell consists of an iron tank lined at the base with carbon, 3 layers of molten aluminium with different densities to prevent their mixing. The upper layer of the electrolyte cell consists of pure molten aluminium with a series of carbon rods that serve as the cathode. The middle layer or the electrolyte layer consists of a molten mixture of sodium, barium, and aluminium fluorides. The third layer is the bottom layer. Along with the carbon lining, it acts as the anode for the electrolytic cell. The bottom layer contains impure molten aluminium obtained from Hall and Herold's process. Using this cell, aluminium is purified in 4 steps. Electricity is passed through Hoop's cell. Aluminium ions from the middle layer reach the top layer and get discharged. Aluminium ions collect at cathode as pure aluminium. At the same time, an equal amount of aluminium from the bottom layer, that is, the anode layer, moves to the middle layer. In this process, 99.98% pure aluminium is obtained. Aluminium is used in a wide range of products, from chocolate wrappers to sophisticated aeroplanes. Let's take a look at some of its common uses. Aluminium is widely used in the manufacture of automobile components because of its strength and relatively lighter weight. In the construction process due to its high tensile strength. In the manufacture of electric wires due to its high conductivity. For the packing of medicines and pharmaceutical products due to its malleable nature. In the manufacture of soft drink cans and espresso coffee makers because it does not rust and is relatively less toxic in nature. In the manufacture of kitchen utensils because aluminium is a good conductor of heat. Extracted aluminium in combination with other metals like copper, manganese, magnesium form alloys. An alloy is a homogeneous mixture of solid solution of two or more metals or metals with non-metals. Duralumin is a light and tensile alloy of aluminium. Duralumin is composed of 95% of aluminium, 4% of copper, 0.5% of manganese, and 0.5% of magnesium. Let us look at some of the common uses of duralumin. Duralumin is widely used in the aircraft industry. This is because of its lightness and other desirable physical properties. It is also used in making pressure cookers to withstand high temperatures. Magnesium is an alloy of aluminium and magnesium. Although weak and soft in elemental state, magnesium combines with aluminium to produce some alloys that are useful in engineering materials. Magnesium is composed of 85% of aluminium and 15% of magnesium. Magnesium is used in the making of balances because of its high structural strength and resistance to corrosion. It is also used in the making of optical instruments like cameras and microscopes due to its light weight and resistant to corrosion.